It's my great privilege to introduce our first speaker of the morning session, Lorenzo Tancredi, who will tell us about scattering amplitudes and Feynman integrals for collider physics.
Okay, so hi everyone. So it's a pleasure and it's an honor also for me to be here. It's my first time at IIS, so I want to thank the organizers for the invitation. It's wonderful to be able to talk about this very interesting topic in this beautiful place. So indeed, what I've been asked to talk about is scattering amplitudes and also Feynman integrals for collider physics, so the collider part of the story. And I want to start with a little bit of a disclaimer that this is not a review of results. So I will, of course, have some citations of some things that I think are important here and there, but it's more like of a personal perspective. So please don't get annoyed if there is something that should be there and is not there. I mean, I'm open for discussion. So it will be a little bit biased, but I will try only to give you an idea of what we are struggling with, what are the issues that we are playing with nowadays. And so since we are talking about amplitudes for colliders, I want to start with colliders. So why still colliders, in particular, why the LHC? I mean, this is a bit of a political question, right, at some point. So because, of course, these colliders are becoming more and more expensive. And so we are asking ourselves more and more, and I think the community is asking us, why do we want to keep on doing colliders? And I think actually the best answer to this question, or one possible answer to this question at least, comes actually from the LHC itself. I mean, if you think about the history of the LHC, I mean, the LHC was born and was made not as a precision machine, was made as a discovery machine. It was supposed to discover the Higgs boson, but also to discover many other particles from supersymmetry beyond standard model particles. That didn't happen, as we know. We only discovered the Higgs boson. But the LHC has been incredibly flexible, actually, and it showed actually also how colliders are actually multi-purpose machines, being able actually to turn itself from a discovery machine into a precision machine. And a lot of the precision program that has happened at the LHC since then has actually been centered, among the other things, of course, on the Higgs boson that was discovered in 2012. And I want to actually take the Higgs boson as a good motivation to start from here, because I think it's fair to say that the Higgs boson is really holding somehow the standard model together, right? So it's doing this both in practice, because it is the particle that makes a standard model a consistent theory, as we know very well. But it also somehow holds the key to the answer to many of the questions that actually we still have about fundamental physics, right? So questions about the origin and the characteristics of the spontaneous symmetry breaking mechanism, the stability of the universe, the origin of masses, of course, and then also questions about QFT itself. I mean, if this is the only scalar particle, is the only fundamental scalar particle, is it fundamental or not? And I mean, all this nice pattern, I think, is explained in this beautiful picture by Snowmass that was made for the 10 years of the Higgs discovery. Now, the reason why actually things are particularly interesting today is because colliders, in particular the LHC and what will come after the LHC, Illumi LHC and the future colliders, are actually opening a window for us on a part of the Lagrangian that we actually have not really completely seen yet, right? So we have seen the Higgs, we have seen all the particle content, but we have not seen yet completely the interaction. We are starting to have to pick at them right now. And one example is, of course, the gauge sector of the Lagrangian, which is the one that we probably understand the best. Is also the one through which we have observed the Higgs boson decaying to diphoton and diz. And it's also the one that is probably theoretically the one that we all like the most. Is very constrained by gauge invariance and gauge symmetry. But of course, there is still a lot that could happen here. For example, anomalous couplings. I will say something in a second. Then there is the Yukawa sector of the Lagrangian, which is actually maybe the most interesting in this particular moment in time, because this part of the Lagrangian is much less constrained than the gauge part. And nevertheless, actually, we are now for the first time in the position to actually observe this. Sorry about that. So we actually seen for the first time, thanks to run 2 at the LHC and the data collected around run 2, we have observed the couplings to all the third family fermions, which was already a very impressive result, to something like around 10 to 20% precision. And we've actually started seeing some glimpses of couplings to the second families, in particular the muon. And with run 3 and high luminosity LHC, we actually hope to go beyond that, to start doing precision measurements and also start discovering maybe some of the couplings to the second family, muon and charms, if we are lucky. Then there is, of course, the Higgs potential. Let me drink a little bit. Sorry about that. And the Higgs potential is actually maybe the most mysterious part of this Lagrangian, because actually also at the LHC and at the Illumina LHC, as far as we know now, we will only be able, with all the data collected, to barely see it, maybe to see 4 to 5 sigma evidence of this, of the triple Higgs coupling, the self-coupling of the Higgs. Nevertheless, these were data and were like ideas that came out from estimates of 2018, and actually experimental techniques are getting better and better. And so as we will see also in a second, there are actually new ideas that one can use. And maybe at the LHC and Illumina LHC itself, we will be able to do better than that. So let's have a look now at these three sectors, right? What do we have to do in order to study and understand them better? Well, if we think about the gauge sector, for example, we're there in order to study this sector better, see if there are anomalous couplings and so on. The LHC is actually doing an incredible job at actually measuring very complicated final states, for example, die boson production, tree boson production, vector boson production plus jet. And as you see from these plots, which are coming out every year, the precision of these measurements is getting better and better, right? And what I want to actually push your attention to, actually to stress for you, is the complexity of these processes. So we have like 2 particles coming in and at least 3 particles coming out. There are massive particles, electroweak couplings, and so on and so forth. Similarly, if you want to prove the Yukawas, well, the way the LHC has been doing this has seen the Yukawa of the top, for example, is through TT bar Higgs production. And there are other similar processes in order to see the bottom, to see muons possibly, and so on. And you see again, what is happening here, we have like complicated final states. We have initial states like gluons or quarks, which are usually massless, but then complicated final states with masses, yeah, everywhere. Finally, for the Higgs self-coupling, for the self-interaction, as I said here, this is the most difficult part to see, even at Illumina LHC. So the classical way to try to see it is observing actually di-Higgs production, right? So these diagrams that you see here. And if you want to observe actually di-Higgs production, it turns out that these 2 diagrams here that contribute and actually allow you to see this coupling actually interfere destructively with each other. And it's the reason why the cross-section is actually so small. The cross-section for di-Higgs production is actually 1,000 times smaller than the one for single Higgs, which is the reason why observing this process is so complicated. Nevertheless, Illumina will collect a lot of data. There will be a chance to see this, maybe up to 5 sigma even. And then there are other possibilities, for example, indirect searches, for example, searching into vector boson plus Higgs, so associated production. And you see that also here you have rather complicated diagrams where you produce, again, massive particles together, 2, 3 of them at once. So this actually, the first thing that I want to say here is that this is just very important actually to realize that on one point of view, it's true that we find ourselves in a special time where for the first time in history, maybe, we don't expect to actually discover a new particle. There will be many new there have been many new particles discovered in the last 100 years, one after the other. And there was always a reason to expect that a new particle would be observed. This is not the case today. The Higgs might be the last one for a long time. We don't know. Nevertheless, there is a lot of potential of discovery, in particular discovery for what concerns the interaction and understanding actually the characteristics and the specificity of this Higgs sector of the Standard Model, which, as I said, is connected to so many important questions. And in order to do that, I mean, to summarize this first section of my talk, we have to understand very complicated processes at the LHC, complicated processes which have complicated final states, with a lot of massive particles going around, electroweak, QCD, massive quarks, massive bosons, and so on. So the LHC is doing a great job at measuring these things. As I said, just with 5% of the data that we'll collect until the end of Illumina LHC, which would be in the 40s, it has already measured many of these processes to the percent level precision, some of them to 10%, but the precision will go down. And so we actually have to be able to keep up with that. And this is one of the strongest motivations that come from Collider to understand complicated scattering amplitudes. So I hope that this convinces you that we have a strong motivation from Collider physics to actually do percent level precision physics. And so how do we do that? Well, actually getting there, as you know very well, from the Lagrangian to the cross-section is actually very complicated. And it's not only complicated because we have to do complicated calculations like scattering amplitudes, we have complicated patterns of infrared divergences and so on and so forth. But it's also complicated because in particular at hadron colliders like the LHC and future hadron colliders, we collide hadrons, which are QCD bound states. And of course, there is a lot of non-perturbative physics that we have to understand. I mean, the buzzword, the important word here is factorization. So we have to understand how low energy and high energy factorize from each other. And we have to understand how to do this actually at very high precision. And there's been a lot of work trying to understand how we go from this picture, if you want, to what we really see at the LHC. A lot of people in phenomenology have dedicated a lot of work to understand the details of QCD. And indeed, there is the hope, and for many cases, we are already there, that we can do these measurements, that we can do these calculations, keeping a precision at the percent level. And this really has to do with understanding QCD, right? So if you think about it, I mean, it's actually a very important thing. Unfortunately, I will not be able to talk about this. It's farther away from amplitudes. But what we will actually do is somehow assume that this has been done. And as I said, unfortunately, I cannot talk about that, but it's important to recognize this. And actually zoom in this picture in what is actually inside that blob, right? Which is the hard scattering, the part of the scattering that happens at very high energy. So where QCD is perturbative, and so where we can try to compute scattering amplitudes in a perturbative series. Let me also stress that actually doing these calculations in here also gives us a glimpse on actually non-perturbative structures, so all order structures, at least in QCD. You will hear something about this also in the talk by Federica. So how do we do these calculations, and how do we get to percent level precision? Well, we just take our cross-section, we write it as an integral over scattering amplitude, and then we just decompose the scattering amplitudes in the couplings, right? So from here on, I will often say QCD. When I say QCD, I think most of the times about the QCD coupling, because it's the largest one of the energies we are interested in, 0.1. Say at the Z mass energy, but what I say also holds for other standard model interactions, right? Electroweak or whatever you're interested in. So we expand our amplitude, right, in the coupling constant. And what we actually do, expanding the amplitude in the coupling constant, is that then we start computing various pieces with Feynman diagrams, typically. So, of course, if we look at the precision, I mean, the first order, the reading order, is actually very simple. It's like 3-level diagrams. Unfortunately, it just gives us a very rough estimate of what the cross-section is going to be, something around 100%, right? So really just the order of magnitude. Then we can go one order higher, and we can actually go to next to leading order, which actually starts involving more interesting patterns. There are like real radiations, and there are virtual diagrams where there are loops, which we have to compute. And if we manage to do that, we actually go down to something like also 10% if we are lucky, or maybe 30%, 20%, depending on the process. So these calculations now are very well under control. I will say little about this, but maybe a little bit more in a second. But it's important to realize that they still don't take us right as far as we want. Then we have to go one order higher. One order higher, of course, involves 2-loop diagrams, more complicated patterns of external radiation that have to be put together in order to get something infrared finite. And it actually becomes also particularly interesting, because on one side, we have the story of the scattering amplitude, which is the one that we are telling at this conference, and I will be telling today. But then there is also the problem of how you put all these things together, right? And how you cancel infrared divergences and you get something finite out of this. There will be a talk by Chiara on this topic, which is also very important, and there have been a lot of progresses. And actually, many of the techniques that we use to understand scattering amplitudes are also exported to understand these patterns of infrared divergences and do calculations that are used to understand infrared divergences. Now, is that enough? Well, typically, actually, it's not. So depending on the process that we are looking at. And I think a very nice example is Higgs itself, Higgs production, where if you compare the leading order cross-section with the Atlas measurement, you see that it's very far away. And then you continue like increasing, adding more and more corrections. You have next leading order, next leading order, but then you start having QCD, electroweak corrections, resummation, then Q below QCD, and so on. And you finally get to something that converges nicely, and is also very spot on the experimental prediction. So in many cases, it turns out what this is telling you that actually you have to go even further. So we have to compute even 3-loop diagrams, or actually 2-loop diagrams with 3 external legs, and so on and so forth. So very complicated calculations. So how do we do these calculations? Now we're going to talk about the amplitudes more, which is of course the main topic of this conference. So A represents an amplitude here for me. And I want to start with the integrand here, because, of course, I think in the amplitude community, from my experience, I mean, I come a little bit more from the phenomenology community in a sense, or collider community. But very often, I mean, in some types of theories like gravity or N=4 super-Yang-Mills, where using Feynman diagrams is out of question, a very important question about computing an amplitude, and what often is intended as computing an amplitude, is actually computing the integrand of the amplitude, right? And this is definitely a very important first step, but it's not the only step, right, that we care about. So there is computing the integrand. Then usually what we do as a second step is that we want from the integrand to get the decomposition of this integrand into building blocks, which are building blocks which are supposed to be simpler in some sense. and they're supposed to be also in finite number and in smaller number, and that we are supposed to be able to compute. And so then devising some ideas and some methods to compute these building blocks, and then finally putting everything together, hopefully getting something that is simple, like, for example, this is a result of the G-2 at 2 loop for the electron. Of course, I mean, these blocks usually, at least in the community I come from, a lot of effort has been dedicated in understanding these things separately from each other. But of course, these are not separate problems, and they are, of course, connected. And if we have a way to find a better integrand, then usually the decomposition becomes simpler. If we understand how to do decomposition into a better basis, then calculating this decomposition, these blocks in the spaces becomes also simpler, and so on and so forth. So, of course, one of the big questions of today, also for our community, is how do we close this circle and how do we actually understand how to do these things properly together? So let me start now from the beginning, from the integrand, right? So at the level of the integrand, as I said, in a sense, in some theories which are not QCD, the problem is getting the integrand not with Feynman diagrams. But what we actually do most of the times, to be completely honest, is actually just using Feynman diagrams in QCD. The reason is because it's true that they are a lot. So if you take like 4 gluon scattering at 3 loops, you have something like 50,000 Feynman diagrams, 500 pages like this one. But this is not really scary. I mean, it's not the number of diagrams that scares us, right? So the problem, of course, is that, I mean, if you have so many diagrams, you can use some clever programming, you can use like, you can be clever in writing down nice computer codes and so on. And so some of these things is really no problem today. I mean, there are some one loop calculations that have more diagrams than that, like hundreds of thousands of diagrams. The real issue, of course, in the integrand is the hidden simplicity. Is the fact that when we decide to use Feynman diagrams, we actually prefer locality, we split things into little pieces, but actually these little pieces hide many of the symmetries and of the simplicity of the final result. And so the calculation, in a sense, in the intermediate stages looks much more complicated than what is actually going to be the final result at the end. Do we have actually anything to solve this? Well, as far as I know, I can tell you what happens on the collider physics side, right? At 3 level, we understand these things very well. We have on-shell recursion techniques, actually also off-shell recursion techniques. The on-shell ones are also the most beautiful ones, like PCFW. At 1 loop, we have unitarity that works in particular very well for massless cases. If you have massive particles in the loops, we also use recursion techniques that are also off-shell. I will say this in also something about this in a second. At higher loops, well, there are question marks. There have been like nice new results, in particular by Nima and collaborators, about how to get the integrands in completely different ways. But the truth is that as far as we are now in collider physics, we just use Feynman diagrams. Yeah? We don't know how to do any better. So this is, of course, a very important place where we need actually to understand how to go further. Now, what about the decomposition? So I will not say more about this, but I want to go to the decomposition because, of course, you could say that okay, maybe we are not doing the most clever thing ever, putting together things with Feynman diagrams, but if we have a way to find a nice decomposition into building blocks which are actually, if you want, minimal and also have the right physical properties, then we could, in a sense, bypass this issue, right? Because we could say that if we have techniques and computers that are good enough, then we might be able, if we know what the good decomposition is, to go directly to this decomposition from any representation we start from. And so a lot of effort, in a sense, has been dedicated also to try to understand this. But of course, I want to stress again that if we start from a simpler integrand, then of course this decomposition will be simpler. Now, this was incredibly important at 1 loop, right? At 1 loop, understanding how to do this decomposition was what triggered one of the main triggers of the so-called next leading order revolution. So that by now we can do any 1 loop calculation or next leading order calculation that we want. And the idea is exactly that every 1 loop amplitude can be decomposed into boxes, triangles, bubbles, tadpoles, and rational parts. And we have very powerful techniques to actually compute the coefficients of this decomposition. As I said, some of them are based on unitarity, others in complicated standard model processes with a lot of masses and so on. As far as I know, the most efficient ones are actually off-shell. They're actually based on recursion techniques on Feynman diagrams. But this is only a technicality in a sense. There are many of these techniques, and it's actually important to realize that both on-shell and off-shell, we can actually get any result that we want at 1 loop. Now, when we go beyond 1 loop, things become a little bit more complicated, but we are lucky in a sense because we are in a situation where despite things being complicated, we at least have something that allows us actually to do these calculations in principle in general. So the type of decomposition that I was talking about before. And these are integration by parts identities. So the idea is that you have your Feynman diagram, your Feynman amplitude you write it down with some algebra in terms of scalar integrals, which you can always do. And then you use really integration by parts identities to find relations among these integrals, and then reduce all these integrals to a basis of integrals. Now, IBPs have like both a good and a bad fame, I would say. Of course, this ended up being, and it is today, a brute force approach technique. So what we do is that we generate all these identities and we actually solve a big system of equations. But I think I also want actually to stress the fact that actually IBPs are incredibly powerful. And actually they also hide, I think, still a lot of information that we should actually try to understand how to actually make them more physical in a sense and extract the information that we need from IBPs without going so much brute force, right? And so the idea is that actually one can prove that, first of all, master integrals are infinite number. They provide really a basis to the space of Feynman integrals, and so also allow us really to talk about this space as a vector space and really do linear algebra, right, in this vector space. As I said, they turned this decomposition problem into a linear algebra problem, which is solving a big system, but this is also not the only possibility. And of course, I mean, they present us with the question of, I mean, you have a basis, of course, different bases might be more or less complicated, right? So it depends on the basis that you choose. And then, of course, a very important byproduct is the differential equation method, which I will say something about later. So the first application, I think, of this method was in 1997, for the, as far as I know, at least in a systematic way, for the calculation of the G-2 of the electron. I mean, at the time, this calculation I know firsthand from Ettore Remedi that had been working on this for like 20 years. It was really like a lifetime calculation, computing one integral after the other, like from the 70s to the 90s. Until finally these IBPs came out and people realized, oh, look, actually we have the result already. We thought that there are actually many other integrals to compute, but they're all connected to each other. And so we can write down this beautiful result like in a few hours. And of course, it's also where Laporta wrote his famous algorithm that is the algorithm that we use now to solve IBPs on a computer. Okay, something happened, whatever. Now, of course, things change a lot from the moment from 1997 to today. In particular, calculations increase factorially in complexity with the number of legs and the number of loops. So the problems that we are solving today have a lot of scales and a lot of loops. And what this means is that in practice, we have to actually handle on computers terabytes of complicated identities, terabytes of or gigabytes or terabytes of complicated rational functions that come out of the solutions of these big systems. So things are extremely complicated. The place where we have managed to get with a lot of advances on the computational side, and not only, is actually doing two-loop 5-point amplitudes. So in particular with three where the particles are all massless, and then there are results or partial results with one massive leg. And I think we will hear something about integrals with two massive legs by Samuel later today. 3-loop 2-to-2, and 4-loop 2-to-1 or 1-to-2 decay processes or form factors. And the way we got there, okay, was thanks to important advancements in mathematics and in computational science, in particular using finite field methods, which allow us to avoid intermediate swell of the expressions and only reconstruct the final results, which are usually simpler. So you don't have to solve these big IBPs symbolically, for example, but you only do it over finite fields, and then you reconstruct your final result at the end. And also algebraic geometry methods, which actually help a lot to reduce the number of IBPs. So practically it turns out that these IBP systems are very large, are way too large. A lot of the identities are not independent. And so actually what we can do is that we can try to think about ways to generate and like a slice in this IBP system and only take the ones that we really need, right? And so you see here that mathematics is actually helping a lot to uncover a lot of structure that is still hidden inside the IBPs. But I think we still don't have the final word on this. And then there is a topic of intersection theory. I won't be able to say anything about this. This is not yet, I think, as mature to compete with the standard methods, but it's very interesting because it really exploits, it's the only method that I know of that exploits the idea of this vector space. So we have a vector space, the Feynman integrals, we have a basis, the master integrals, and we can actually really define a scalar product in a complicated way, unfortunately. Also thanks to Sebastian, actually, it was one of the first people to work on this, to actually project Feynman integral onto master integrals directly. If this were to work out in a say, systematic way that we can apply also to complicated processes, it would be a completely different point of view on this. It is already a completely different point of view on this. And so I think it also still holds a large potential, which is still to be explored. Now, about this decomposition itself, of course, I talked a lot about the computational advances, but there are also interesting advances from the point of view of actually how do we choose the integrals, right? It's not only how do we do the decomposition, but we have to know what to decompose into, right? And of course, one very important thing and a lot of important ideas came from N=4 super Mills. In particular, from the idea of local integrals, it was introduced by Nima and Jake and other people in the audience, where we've actually learned that there are some nice type of integrals and integrands which actually encode the logarithmic singularities locally, the logarithmic singularities of the amplitude. These are pure and uniform transcendental weight integrals, and they are very beautiful. They're also very beautiful to compute, not only to decompose the amplitude. So this was definitely very powerful. And another thing that is also important that we are struggling a lot with today is actually realizing, where we know this very well, that simplifications only happen close to d=4, not for general number of dimensions. And so there is this issue with dimensional regularization. I mean, the dimensional regularization is beautiful because it allows us to do incredibly complicated calculations were impossible before, but it also hides this simplicity in a very convoluted way. I will say something in a second about this. So is it good or is it bad? Well, I don't know. But definitely, I mean, a question that we actually are asking ourselves is whether there is actually a more clever way to define finite remainders, which are actually more physical, what is the most physical type of definition of finite remainder, and how to get there as fast as possible, in a sense. And now about why DIMREG is good or bad and what are the issues, I mean, you're probably all familiar with this, but I want to stress where the problem is, which is actually something that if you go back at one loop, you learn that actually you realize that at one loop people knew better and actually were not doing this. This decomposition that I talked about at one loop is actually not really an independent, unique decomposition as far as integration by parts identities are concerned. The classical example is the massless triangle, which can be reduced using IBP reductions with a rational function that depends on the p-squared, 1/d-4, and a bubble. Now, if you look at this type of identity that you will put in here and maybe remove the triangles depending on the process that you're looking at, this identity, what it is doing is that it's actually swapping a overlapping soft and collinear divergence in the triangle into a UV divergence in the bubble times a 1/epsilon. So this is, if you think about it, it's as ugly as it can be, right? And so you're not surprised is if you do that the amplitude will be decomposed in terms of this bubble, and somehow this bubble will have, through its coefficient, remember that there is something infrared in it and something UV in it, right? So this coefficient will have a very complicated dependence on epsilon and will be very ugly, yeah? So, of course, one thing that we are actually realizing and we are thinking about today is that, of course, first of all, QCD, unfortunately, is not N=4 super Mills. So it's more complicated. It's not UT and it's not pure. So these local integrals are, of course, very powerful and very nice, but they might not be the best way to represent an amplitude. They might be the best way maybe to compute the amplitude. This I will get this in a moment, but it might not be the best way. And there are examples where, and I think David will talk a little bit about something that goes in this direction, where if you choose your integrals following different criteria, for example, infrared finiteness, separating infrared and UV as much as possible, and so on, then you can get also for two-loop amplitudes. This is an example for a all-plus amplitude for 4 gluon that I got from Giulio, hoping that is correct because it's not published anywhere. But it's just to say that if you choose the right integrals, the coefficients become super simple in front of the integrals, but you have to choose the right integrals. If you use a canonical basis of local integrals in this case, then the coefficients become extremely ugly, okay? And this is important also to remember. Now, in the last 10 minutes, or 5 plus, I don't know, I want to actually talk a little bit about the integrals, okay? Because I talked a lot about the decomposition and what are the issues for me in this decomposition, things that we should be thinking about. So what about the integrals? So for what concerns the integrals, I think there are 2 points of view that are the main point of view that we usually have on Feynman integrals. One is the one of direct integration. People like to think about Feynman integrals by direct integration, for example, using Feynman parameters, or a similar representation is the one by Lee and Pomeranski, where there is one single polynomial in this thing, but I mean, they are equivalent. Now, from the point of view of the integrals, we want to compute these integrals. And so what actually we can learn from this point of view, and we will see in a second also from the other one, is that actually there is always an algebraic variety under, if you want, the definition of these integrals. And when we compute these integrals as series expansions close to d-4, then what we're actually going to get out of this is actually iterated integrals over, well, differential forms that are defined on specific algebraic varieties, which are defined by these polynomials, by the zero of this polynomial. A similar point of view, actually, to think about this, It's from the differential equation method. So you might have heard about this, most of you. So the idea is very simple of differential equations, is that using integration by parts identities, you can actually prove that if you differentiate the integrals, you're going to get same type of master integral, same type of integrals, which are not masters anymore, it's their derivatives, but you can use the IBPs again to rewrite them in terms of the masters. And so you get a nice system of differential equations, linear, where this matrix here is actually just a matrix of rational functions in the dimensions and in the Sijs or the masses or whatever you have in your problem. Now, what turns out to be the case also here is that this is a big matrix. If you go close to d equal 4 or to any even number of dimensions, because of course the even numbers of dimensions are connected, then you actually discover that the homogeneous solutions in the different blocks of this matrix for the different sectors and the different types of integrals actually determine the complexity of the problem. And in particular, what they tell you is that they are usually, typically, are periods of algebraic varieties. Again, so for example, periods of an elliptic curve or periods of a Calabi-Yau and so on and so forth. Now, the simplest of all the algebraic varieties that you can think about is the sphere. In the case of the Riemann sphere, things are actually very simple. There is really nothing difficult, no complicated periods happening on there. The only thing that we have on the Riemann spheres are actually poles. And if the poles are double poles, when you integrate them, you just get a rational function again. If they are single poles, you get a log. And in fact, the generalization of this construction actually brought us the multiple polylogarithms, which are an incredibly powerful space of functions. Why? Well, because we can actually generalize this even more to saying these don't have to be like single poles rational functions, but they have to be just dialogues, so maybe even algebraic functions. These are chain iterated integrals over D-log forms, the further generalization of this. And in a sense, this is the very natural space of functions onto which you want to integrate the local integrals that we were talking about before, because local integrals have only logarithmic singularities. They are written as a series of D-logs. So of course, naturally, they are exactly this type of integrals, right? And I mean, differential equations in these cases can be put in a very nice form, which is by now called the canonical form, which was done by Johannes Henn and also other people worked on this, where actually this structure is very manifest because you see that you have the differential, you have a d-4 in front, and then a lot of d-log forms in here. Yeah. And I think Samuel will also talk a little bit about this for his calculation that he's going to present later today. So as I said, Masters QCD profited a lot from this, but of course, this is not the end of the story, right? So there are many other complicated things that can happen, unfortunately, and they happen already in the simplest thing that you can imagine, say the two-loop electron propagator. This is a calculation that was done in the 60s, attempted in the 60s by a student of Cellen. Cellen had computed the two-loop photon propagator and then told the student to compute the two-loop electron propagator. And of course, this revealed to be much more complicated. The reason is because if you cut this diagram and you look at what happens inside this diagram, well, you find the famous sunrise integral, which is written in terms of an elliptic integral, at least it's cut, this imaginary part. And this, unfortunately, turns out, or fortunately, I don't know, turns out to happen all the time. There are like, at least in QCD, as soon as you have masses, even in massless cases, even in n=4, but in QCD, it happens very soon. If you have like diagrams like these ones, which are the ones that we are dealing with every day at the LHC, they are full of this elliptic stuff. There will be a talk by Francisca that will actually tell us something about diagrams of this type. What I want to say here is that the elliptic thing is only one part. As I said already, hinted to before, the landscape is much larger. So we know about elliptic, we know about Calabi-Yau happening if you start, for example, computing the QED electron propagator to higher loops or electroweak corrections to different processes. And we know also about higher genus that can also happen if you already have two loops, actually, if you have enough masses inside the diagrams. So the panorama is very complicated. The landscape is very complicated. And so one possible point of view here would be to say, okay, I mean, we don't care about this. We actually try to, I mean, there's something missing in this slide. There was something down here, but okay. We actually try to do these calculations numerically. Sorry about that. I mean, there were some other examples of numerical calculations and also some citation. I will fix the slide. But the important thing here is that what I want to say, there are numerical methods. I won't talk about them, but people are doing also a lot of progress on the numerical side because, of course, if you want to get a number out of this, you have to do something. And there is a lot of progress, but these things, of course, are not easy. They are complicated. And a couple of open questions that I want to stress before closing. I'm almost at the end. Whether you want to use numerical or analytic method, I think that the question remains, and it is the question that connects all this big circle that I had at the beginning, namely, what is actually, what are good integrals? What are nice integrals to compute? There are many people that have been working on this, also again in the audience. There has been a lot of progress, in particular from understanding how these integrals, when we go beyond d logs, actually look like from the differential equations point of view. We and also other people have been working on defining some generalizations of this epsilon factorized basis in these cases. But what actually is important there to realize is that actually mathematics is telling you something new, and how to embed this new information into physics is maybe the interesting question. Mathematics is telling you that if you go beyond the Riemann sphere, and so beyond d logs, you actually have higher poles. Higher poles are part of the cohomology of the surface that you want to describe, right? For example, on the elliptic curve, there are actually double poles. There is nothing you can do about that. So the question is actually how to choose nice integrals, and how these double poles will actually show up in a sense and cancel, because they have to cancel, of course, in the scattering amplitude, in some sense, or in the physical quantities that you want to compute. Now, an example of this, just very brief, is a calculation that we have been working on, but just to say a word about what actually could happen and where things could go. If you try to compute the propagator of the electron, which is not even a physical quantity, but nevertheless three loops, you find a lot of elliptic sector and a lot of stuff. And so there are a lot of elliptic sectors in here, which actually are related to forms of the first kind on the elliptic curve, which have no poles, of the third kind, which have actually single poles, sorry, and that the generalization of the d logs, and then also forms of the second kind, which are actually objects with double poles. And what turns out to be the case in this calculation and also in others, which hopefully we will finish soon, and also I think other people are working on this, is it actually turns out that the forms with double poles turn actually always to be suppressed by an order in epsilon. So actually not to really show up, not in the full glory, at least in the finite part of the amplitude. And so an interesting question that I find interesting, and I think one could try to think about, is how to actually generalize this and understand if there is a way to project directly only on the integrals that we really need, again, in d = 4, right? So it's very important that simplifications happen in d = 4. Now, this brings me to my conclusion. I think I'm done. So I hope that I managed actually to convince you more or less in time that, first of all, colliders are important. They remain actually the most flexible and I would say multi-purpose experiments to investigate fundamental questions in physics. And they also still have a lot to tell us, right? Next generation colliders, also the LHC that is running now, have really a guaranteed outcome, which is like discovering the Higgs self-interaction, measuring the Higgs potential, and we don't know, right, what else will happen. Now, what actually I find it also particularly interesting for this community is that collider physics actually obliges us, so forces us to have to do with very complicated problems, not nice amplitudes or everything is massless, planar, and so on, but complicated like amplitudes with masses, with vector bosons, with tops, electroweak couplings, and whatever. And this is actually a huge challenge for me, and a challenge which I hope also the whole amplitude community wants to take. And I think actually this is what is happening, right? Because we are talking a lot to each other. And so we have already learned a lot. I think the collider community has learned really a lot from the n = 4 community, from string theory, from CFT, to actually try to do these calculations better. We are now at a point really where we are really able to talk to each other, and I think that this is extremely exciting. So let's keep exploring together, and remember that collider physics is cool, even if colliders are expensive, unfortunately. And so thank you for your attention.
Thank you, Lorenzo, for the excellent review. We have time for a couple questions.
So you mentioned Laporta's algorithm, and that it took like 20 years to do this calculation, but there was a concurrent development in mathematics community, namely by Gelfand and his school on hypergeometric systems, and IBPs were known there. And there was even older development on the restriction of flat bundles to subvarieties in terms of for B functions. That's by Kashewara and Bernstein and others. That is from the 70s, actually.
Yeah.
So why do you think it took so long for physicists to rediscover these things?
I don't know. It's a difficult question. I don't know that they were aware of this, right? And also, I think this is a practical, also it's a type of, so what people have been trying to do. So hypergeometric results, I think, are important. People are also rediscovering them now, right? A lot of this theory, right, of hypergeometric functions. So at the time, to be honest, I don't know if they were aware of this. I think they were not. I also don't know if it could have been used with the same simplicity as this type of techniques in order to get this result, right? Because of course, I mean, the Laporte algorithm has this nice thing that you can put it in a computer, you can push a button and you can just get the result, right? That's, I think, the only thing that I wanted to say about that. But of course, maybe there were other ideas at the same time. Yeah.
Thank you. Lance?
Thanks for this great talk. One other, you mentioned non-uniform transcendental combinations of integrals. I think that's also very important as you try to simplify non-n=4 or QCD expressions that have huge numbers of spurious singularities in many different channels. It's not even clear whether a basis is the right thing. You maybe should be over.
I agree.
To take this into account.
Look. I mean, I was a bit fast on this, but you're right. I mean, thank you for the question. Thank you for the question. Indeed, I think the kind of basis that I'm showing here, sorry, I was a bit fast. So thank you for the question. Then I can explain this a little bit better. This is not it's a unique basis from the point of view of IVPs. So one can think about different things in this direction. One thing that one can think about is if you can take only again slices of IVPs that don't mix infrared and UV. For example, this is kind of a question that we are thinking about, and I completely agree with you. So I think if you go to a minimal basis, is also the reason why I showed the triangle, right? This means going to a minimal basis, and it means like messing up everything. If you don't do that, then actually the structure is much simpler, which is what people have been doing at one loop, right, all the time already. Yeah.
Let's thank Lorenzo.
Thank you very much.